Welcome everyone to our next GoAERO expert lecture. We're so pleased to have you here with us. Um, as always, we're so pleased to be joined by our sponsors and supporters, including organizations like Boeing, NASA, RTX, and many others. And we're so pleased to be supported by so many organizational partners around the world, including AIAA, AUVSI, space faculty, AOPA, and organizations all around the world. We're so pleased to have Simon Gharibian here today with us. He's the Director of Global Sustainment Centers of Excellence at Lockheed Martin. He is he's responsible for all functional resources within the Global Sustainment Organization, with 6 COEs delivering traditional sustainment products, including technical publications, training, logistical support analysis, O&R, depots, spares forecasting, and field support. These support the entire spectrum of RMS products, from undersea warfare platforms to Sikorsky helicopters. In this role, he is also primarily responsible for the development and deployment of cutting-edge sustainment tools, technologies, and the process to all RMS product lines, as well as partnering with other business areas across the Lockheed Martin enterprise to identify opportunities for sustainment technology synergies. He holds a Bachelor's of Science in Aerospace Engineering and a Master of Science in Mechanical Engineering, both from Syracuse University. So it's my pleasure to introduce Simon to begin our next lecture.
And it's not letting me share.
Oh, sorry about that. Let's see if we can fix it. Here we go.
That works. Okay, so thank you. Thank you very much for that wonderful introduction, and thank you so much for the opportunity and the time that everybody's taking to listen to me give this talk titled "Design for Aircraft Maintenance." I will say that I've sort of modified that. I've actually want to call this more about design for sustainment. There's a little bit of a distinction there. But before I get started, I figured I'd tell you a little bit about myself. They did a nice job at reading off my bio. So you know my educational background. While I was at school, did some fun things like build little race cars. I had a specialization in composite materials, which made me interesting to Sikorsky aircraft, is where I started my career as a design and stress analyst for the Rotor Systems organization. Did that for a few years and then joined what it's now called Sikorsky Innovations. Back then it was called Advanced Design and Business Development. So did some kind of neat conceptual design work on crazy things like variable diameter tilt rotors and some other fun aircraft concepts and pursuits at that time. I actually then left Sikorsky and United Technologies to join a small kind of company that was starting up in East Hartford, Connecticut, doing some kind of high-end structural analysis consultancy work, primarily for Pratt & Whitney, called Quest. So did a lot of different fun finite element modeling and stress modeling for jet engines and fan blades, and actually worked on the Joint Strike Fighter engine at the time, and did some other interesting things, but eventually took advantage of the opportunity to come back to Sikorsky. Joined them again back in 2007 on the 76D program, which was the smaller commercial helicopter. And after a couple of years there as a lead engineer, I joined Sustainment. Started off as running a repair development group, which was quite an education from an engineering perspective to see how things break and see if we can fix them rather than throw them away. And I've been in Sustainment ever since. You can kind of go through So I think that if you do the math, it's 6, 7, I've lost count, right? 12, 15, almost 17 years in sustainment. On the side, I'm very active in NATO from an industrial advisory group standpoint. I'm currently chairing a study group on rotorcraft modularity. I've been in several other studies listed there. I did a stint on the Department of Commerce TransTac, which does things like export regulations. So a lot of export reform at the time. And then on a personal side, I've got two kids of my own, two stepkids, so four of us in total with my wife. We have a boat named Telltales. I've done some stuff with cars. That's the car I built in my garage over 3 years. And then I did a restoration on an older Alfa Romeo, and that'll be relevant in later parts of this presentation. I have a very large dog named Shamrock, who's nearly 160 pounds, so he's almost like a fifth child. And at one point, I did own a horse named Cody. That's him in the middle. So that's me in a nutshell. So back to sustainment. So designing for sustainment, right? Why, right? So designing for sustainment, I think, is a very critical aspect to um, platforms that are going to fly, right? In my world, it's typically aerospace and defense. So sustainment is all about keeping a system reliable and maintainable throughout its life cycle. And I think the theme, if I had to call one theme through this entire presentation, would be um, start now, right? Start thinking about sustainment right from the beginning. And, I'll show you why that's important, but it is absolutely the number one approach to ensuring that you have a sustainable, reliable, and maintainable platform. So we'll talk a little bit about why starting early is important. And then we can talk a little bit about some kind of best practices and strategies to ensure that, as you think about sustainment, as you incorporate sustainment into your design process, into your systems engineering process, how to be successful there. But ultimately, just like any other engineering, it is a balance, right? And so that's one of the reasons I use this cartoon. Love it. It's pretty old. I don't even know how old it is, but it says that look, you can't all do you be 100% about sustainment, right? You'd end up with an aircraft with way too many access panels, etc. But there is a balance, and I think we'll show that sustainment, reliability, maintainability is a very important aspect of your design trade, and you got to make sure that it's incorporated early. So why? Why do we care? Well, now I've made the assumption that the solutions for GoAERO. I mean, obviously I'm from a helicopter background. I'm making the assumption that a GoAERO platform is typically something we would call vertical flight, and with vertical flight comes the complexity of essentially defying gravity, right? Beating air into submission is one of my favorite sayings. The other one is, yeah, a million parts rapidly rotating around an oil leak waiting to happen, waiting for metal fatigue to set in, right? So why, those are funny but true, right? And if you look at the chart on the right, it drives cost, right? So when we look at the total life cycle cost of a platform for any aircraft, but rotary in particular, you're nearly 70% of the cost of that platform is associated with operation, right, and support. So it's happening after the platform has been built, after it's been purchased, and now it's in operations. And 70% of those costs, of the total program costs, happen once it's in service. And so when you look at those components of the life cycle cost, you realize that having a eye on sustainment and designing for sustainment and trying to minimize sustainment requirements of a platform um, has a lot of return on investment because it is the dominant factor within the total cost of the program. And what we also see is that trying to implement sustainment and maintainability, reliability after you've already built your platform or designed and built your platform is a very expensive way to build in sustainment, maintainability, and reliability. Um, you've got to embody sustainment early. So if you look at this chart, you can see that, you know, 90% of what we call the committed life cycle cost. So basically making decisions that are going to drive 90% of the cost for the overall life of the program occur before you've even started production, before you've even built anything. Um, and typically you've only spent about 20% of the total cost of the overall program. So if you're not making good decisions early on in the design process, right up front in the concept and design stages of the program, you're locking in cost for basically the rest of that program's existence. And now I know with GoAERO devices that may be probably a little bit shorter, but when you think about some of the products that I've worked on and I'm a part of, such as the Blackhawk is literally going to be around for 100 years, right? First flight in the 70s, 1978, and you know, expected to fly per the Army well into up into about 2070. So almost 100 years. So decisions that were made in 1975 on that affected the sustainability and the maintainability of the Black Hawk will be paid for through 2070. Just think about that, right? So some of these life cycles can be very long. So, you know, it's important to understand your platform's concept of operations. So in the case of GoAERO, I think we know what that is. And also, you know, what your customer values, right? What do they put importance on? And most customers today, and actually, if you look back in time, have a predominant operational sustainment segment, and therefore they value that when they start looking at a platform, evaluating a platform, and deciding which platform they want to go with and develop. Right. So um, the more you can do early, the better off you can be. So what does that mean? So that means you've got to establish um, sustainment as part of your systems engineering process right from the beginning, right? And you've got to ensure that you've got resources on your engineering team, or if you're a small engineering team, somebody has taken the lead in key disciplines that help drive sustainability and maintainability, reliability, and some of the associated technologies and tools into the platform, right? So I've listed the key kind of disciplines I believe are important from a design team perspective. But the bottom line is, right, we've got to ensure that we've got our heads in the right place, whether that's the right people in the right place or people that have knowledge or at least thinking about these topics as part of your design team right from the beginning. So when we dive into these types of disciplines, well, what are they, right? When we talk about the term reliability, right? What is a reliability engineer doing? So in the context of designing a vertical lift platform, right? The reliability engineer is the one that's driving a requirement. He's saying right from the beginning, he or she is saying, this is how reliable our platform needs to be. These are the goals that we have. And then from that high level goal, breaking it down and looking at all the constituent parts within the platform and applying requirements to each one of those constituent designs, right, and allocating it. And then just like you would measure other attributes of a design as you're going through your design process. So think about other key performance parameters like weight or cost. Um, we typically track those things over the life cycle, or I'm sorry, over the life of the design process, right? And those attributes are measured and tracked, and we take corrective action if we see the predictions of those attributes going awry. Well, sustainability attributes, reliability, maintainability, those need to be attributes that are tracked just the same as you would weight, um, or any other key performance parameter during that design process. And by doing that, um, by setting those requirements, the reliability engineer sets the requirements and then tracks it over the life cycle or over the design process life cycle, and ensures that you're staying on track. And that's one of the ways that you can build reliability into your designs, right? Some of the other things, right, looking at things that might have life limited components, derating your components to ensure longevity is another one. Typically, rotorcraft or vertical flight platforms are extremely hard on materials, on electronics, on propulsion systems. They vibrate, they shake, they move around, and they operate in very challenging environments, tough, from a dust and temperature standpoint. And so all of those sort of things drive a need to derate your components so that you're not pushing them to the limit. And so again, a balance against performance and cost. But if you want a reliable design, you do need to build in a certain level of conservatism, to assume that things will degrade and eventually fail. Uh, Maintainability is another aspect, right? Another aspect of the design process. I put down the bottom, right? Empower the guy who turns the wrenches. And as you might have seen, I put some funny graphics in each one of these slides because I think it is true, right? And as you can see from my who am I chart, right? I'm into cars, I'm into fixing cars, building cars, etc. And that picture at the bottom there, you know, I believe that's a Toyota, which they're actually known pretty much for their reliability, but they had a notorious tendency to put the starter motor in the V of the engine. So for those of you who are car guys, you'll recognize that's a V8, and the starter motor is right in the middle. And so you're taking off the intake, you're taking off all sorts of things to get at it. So not the most maintenance friendly design. But there's other practices, and you need an advocate to implement and speak for those practices in your design trade discussions, right? And so that's what your maintainability guy is supposed to be doing, right? He or she is the one that is sitting there and saying, nope, you really need to make that accessible. That's something that I have to be able to get at. That's something I can't fit a wrench into. I can't get my hand around it, et cetera, right? And so, you can read all this, but at the end of the day, you need to empower on your team somebody who is advocating for the poor individual that's got to be turning the wrenches, bruising their knuckles, and able to actually do the maintenance. They need to be part of that design discussion and ultimately have a say in the approval of engineering changes. And then another aspect to designing for sustainment is ensuring that you have the logistics. So we call these logistics or logistical support analysis folks. Some of their key activities are things like level of repair analysis, right? So again, I always refer back to people's cars, but at the end of the day, somebody has to decide what is an LRU in a platform. What is that repairable unit? Is it the air conditioning compressor in your car, or is it the valve inside the air conditioning compressor? What is the item that the maintainer can remove in the field, is expected to be able to remove in the field, has the tools and technologies and instructions to be able to remove in the field? How far down do you break your product such that it's maintainable? But there's always a balance, right? In terms of complexity, in terms of special tools and knowledge to disassemble things. So again, when you think about somebody's car, you might not want a mechanic in a shop breaking apart an air conditioning compressor. You might want them to just pull the entire compressor and send that back to a depot and just replace it with a new one. However, that drives cost and logistical challenges versus the smaller constituent part. And so anybody who's played with cars knows this balance, right? Um, and and you've got to make intelligent choices and balance that against your ability to provide instructions, provide material to that level, etc., right, and balance it from a logistical standpoint. And so some of the other attributes to a logistician on a design platform are listed here. And again, all of this stuff gets done at the early stages. You're looking at it, you're taking these things into consideration as you're coming up with your conceptual designs. And just like we say, build before you build, right, in the virtual world, or engineer before you engineer in a digital way, sustainment can be the same way. You have to be able to model what you believe the maintenance and spare parts requirements are for a particular design, and then as your design changes and as things progress, you update those models so that you can see kind of where your sustainment costs are going for the overall platform. And then one more recent, and this is becoming more and more powerful, especially as we start to get into machine learning and artificial intelligence, is the prognostics and diagnostics capabilities. So these days, especially on vertical lift platforms, if you're not doing some degree of diagnostics and prognostics, you're behind the eight ball, because as much as we like to think that we can predict everything and we can model everything and everything's going to be perfect from an engineering perspective, that's never the case, obviously. And so the ability to build in prognostics into your design, again, very early, and understand the mechanics such that you can detect at an early stage the degradation of components and give a warning signal to your operators that something is degrading and eventually will need some sort of maintenance, is how prognostics turns unscheduled maintenance into scheduled maintenance. Right? When we think about bigger platforms, or in the case of GoAERO, platforms that are intended to be used in emergency situations, you're talking about platforms that it's a real problem if you go to turn it on, you go to fly in a high stakes environment, in a high stakes situation, and you have something that's non-mission capable, right? That's inoperable, that doesn't work, right? So again, I go back to people's car, right? You get out, you got something really important, you got a job interview, you got your first child's on the way, etc. It's unscheduled, right? So what you want is the car saying, "Hey, I believe there's something degrading. You might want to change the battery or change the alternator or whatever." And you do that on the weekend. You take it to the shop well ahead of time so that the moment you need that car and you turn the key, it's going to actually work. And so it's the same thing from a rotorcraft perspective. If prognostics can help you predict when your component's going to fail, then you can get ahead of it. You can schedule it. You can move materials and resources and people into the right place at the right time, fix those things before they become a problem, so that when it is time for that device to really work, it is there and available. And so, some of the charts I've got on here, just some data from places like Goodrich and other places that do health and usage monitoring systems. On the Black Hawk, they've demonstrated time and time again the significant reductions they can get from ensuring they have a robust prognostics capability on the platform. And so when you want to build this into design, it's a lot easier to do it as you're developing your concept, as you're building it into the platform, than trying to slap it on after the fact. So, I mean, the moral of the story is that one of my leaders has this expression of like, "We are the people we've been waiting for." It's kind of funny, but it's true, right? So there's nobody else that's going to do this. This is all on you. So as you're designing your platforms, right, you have to be the ones to integrate sustainment, design for sustainment into your design teams, into your thought processes, and into the methodology um, and the systems engineering that you do on these, during your design evolution. And so you'll find, unfortunately, just like anything else, from an engineering standpoint, that there is a tension. Right? Life cycle. And typically, what you find is that if you're doing something that improves maintainability, reliability, it's probably, for most of the time, it's probably more expensive from an acquisition standpoint. It probably imparts additional weight and cost, um, which translates into a higher price for the platform itself, right? When you think about what I said earlier about derating components, that means generally you have to have things that are thicker, things that are oversized electrically, for their use. All of those things drive cost and weight, right? But at the same time, they also drive reliability, and perhaps putting something in an accessible spot, or putting in a door or an access panel, again, drives cost and weight, but it allows for maintainability. So it's a balance. And that's why the systems engineers understanding their requirements, um, and then building it into key performance parameters that you measure and check are very, very critical. Some of the other things I'll foot stomp is, level of repair analysis is very important, right? Understanding what you think is the LRU. In some cases, the entire device is the LRU. In other cases, you want to break it down. And so you've got to make those trades so that you are balancing the ability to repair in the field with cost and complexity. And then you got to understand what your customer's mission is and what their priorities are. I know it's probably a little bit racy to put that graphic on there, but in that case, in the middle of Ukraine, that's a one-time use device, right? Sustainment's probably not much of a KPP of that particular item. However, there are definitely other platforms out there that need to come home. They need to operate it day in and day out, and they need to be ready to deliver and perform when the time comes. One of the sayings I like to use for rotorcraft and vertical lift is, yeah, you really are demanding Formula One performance, but Toyota Corolla reliability. It's very true. You expect this thing to work every time you get in it. And lastly, I'll say that, you need to learn from the past, and that's I'll touch on this in another slide, but that's one of the probably more difficult aspects of some of the newer air mobility designs because there isn't much of a past. But looking at failure modes, looking at the way things have broken. That's why I said one of the most entertaining and interesting aspects of my career has been being a repair engineer, being in the overhaul and repair shop and seeing how components fail, seeing how things degrade over time, seeing what things did not hold up, what design assumptions were not very good, what materials corroded, what happened when you combined, stainless steel, aluminum, and salt water, right? Galvanic corrosion set in, or what happens with stress corrosion cracking, etc. Those sort of things you have to learn from, so that when you're designing, you're designing out some of the maintenance issues, sustainment issues that have occurred in the past, right? So for folks that don't have 90 years of design history to lean on, like a Sikorsky, you're going to have to do a lot of research and understanding of like, okay, what are typical failure modes in the platforms that we're designing, the components that we're designing, the materials that we're using, and how do I avoid those issues, right? Something as simple as choosing the right coatings, choosing the right anti-erosion compounds, choosing the right materials in contact with one another, and assuming that moisture and external environmental contaminants are going to get in there, and what happens when you mix that all together. You've got to factor that all in when you're doing design for sustainment. Um, Ultimately, the takeaway is that there is no silver bullet, right? There is no one thing that you can do to make your design ultra reliable, ultra maintainable, ultra sustainable, right? It's all little things. It's all little improvements. And if you're trying to do it after the platform is designed, you can only do so much. So it's got to occur early. And when you do, there are plenty of case studies where improvements and in sustainability and design for sustainment have resulted in remarkable results. So this is an aircraft that's near and dear to my heart. It's the S-92. It's the first thing I ever worked on in my professional career. And I say sort of a digital environment because that was back in the day that CATIA and the 3D CAD environments were pretty new. It was this aircraft and the Boeing 777 that were some of the first to use CATIA in their design. And I do remember walking into Sikorsky and being in the area for the S-92 design team and them having a big board on the wall with all the tools, literally mounted on this big like plywood board. And the rule was, anything you designed with a fastener had to be able to, be dismantled with a tool that was on that board. And if it wasn't on that board, there was a conversation and an exception process. And those sort of mentalities were key to the design and development of this platform. It was intended to be an aircraft that offshore oil operators used as a piece of capital equipment to move people back and forth to oil rigs. And so as a result, they aren't making money unless the aircraft is flying. And if it's not reliable and you've got to do a lot of maintenance to keep it flying, that's all cost. And that eroded the value proposition of this platform. And so, those statistics at the bottom are not made up, right? This fleet of aircraft has amassed over 2.2 million hours. First aircraft delivered in 2004. The high time, what we call the high time aircraft, so the aircraft with the most flight hours on it, was delivered just in the beginning of 2006. So if you do that math, it's flown 30,000 flight hours since then. That works out to 1,650 hours a year, every year for 18 years. Right? Break that down even further, right? 4.5 hours a day, or 6.5, almost 6.5 hours a day if you're only on the weekdays. But that aircraft for 18 years, every day has been flying, right? And so outside of that time is when all the maintenance has to occur, and any and all unscheduled maintenance would have to occur, etc. And so a very remarkable record, and a demonstration of what can be done, um, not only when you design for sustainment and keep sustainment in mind right from the beginning, but then you implement sophisticated health and diagnostics and prognostics capabilities. That's the inset picture, right? We have a whole commercial care center dedicated to keeping these aircraft up and flying, responding to grounding events, responding to urgent needs for parts and technical questions, etc. Right? And so when you back up a solid design with the sustainment support required to keep it up and flying, you do end up with a extremely high performing platform, right? And so then on the military side, right, the 53K is another great example, because the 53K is essentially an upgraded, it's a new variant of a venerable design, 53 Echo. And when the Marine Corps came to Sikorsky, they put in a number of KPPs are centered around maintainability and sustainability of the down things like direct maintenance cost and maintenance man hours per flight hour. And so, again, another platform where all of the things I just talked about were implemented right from the beginning. In addition, a number of task forces were put together that worked in conjunction with the customer to understand, at nauseating levels of detail, the historical failure modes of the prior platform, the 53 Echo, and what went wrong, what were the reliability issues, what were the maintenance drivers, et cetera, et cetera. And then as this aircraft was being designed and developed, that team scrutinized those designs and ensured that maintainability and reliability was baked in from the beginning, right? And then we layered on the benefits that come from using a digital twin for the aircraft and enabling things like condition-based maintenance, which means you only fix things when you need to, right? Um, Reduced the direct maintenance costs by almost half, the maintenance man hours per flight hours by almost half, while lifting 30% more and doing it at almost 20% higher gross weight. So amazingly capable aircraft. You can look it up. There's some neat videos on YouTube of it flying around, but this is an 88,000 pound airplane. So to be able to do that, a large and complex machine, and get these types of results is an indication that designing for sustainment is a very powerful thing when you do it properly. So the last chart I'll end on is kind of something I added in here because of the GoAERO competition is in most cases, I'm going to guess that most of these platforms and concepts are going to be utilizing electrical drivetrains. And one of the challenges that keep me up at night from a reliability and maintainability standpoint, and how we're going to deal with this in the rotorcraft world, is that we don't have 90 years of history for these drivetrains. When you look back, we can lean on 90 years of history for the black to when we designed a Black Hawk replacement or some other rotorcraft. We can see historically what happens to gearbox, to turbine engine drivetrains, and prior to that, reciprocating engine drivetrains. Well, in an electrical propulsion aircraft, all of that goes away. You generally don't have a gearbox. You don't have articulated rotor systems. You don't have um, complex drivetrains and bearings and shafts and all the things that come along with a traditional rotorcraft design. However, you layer in a whole different and new level of complexity and components, right? You've got high current, high power electronics, power distribution units. You've got heavy gauge wires with, in aviation, you're trying to keep things as light and thin as possible. So you're pushing the envelope from an insulation standpoint. You've got potentially, a much more magnetic interference than you might have in a traditional aircraft, right? Because you've got massive motors spinning around and lots of current flowing through wires. Um, Batteries. We've all seen the images and photos of the electric vehicles catching fire, or the precautions that the airlines take so that you can't bring a lithium ion battery on the airplane without it being able to fit in a fireproof bag, etc., right? Because they're worried about thermal runaway, right? So there's failure modes and effects that uh, come with an electric drivetrain that we just don't have a lot of history on from an aerospace standpoint. And I think, if you go and look at the statistics, this is bearing out even in the electrical vehicle world. EVs are not necessarily as reliable as internal combustion engine platforms today. I have no doubt they'll get there, but right now they're not, and I believe a big part of that is because they just don't have the historical knowledge of how to design for sustainment. And so when you're doing it in aviation, it's even worse, right? There aren't really any production electrical drive, vertical lift platforms out there today beyond, small stuff. So how do you make sure that as you're kind of delving into this new world, that you're making sure that you've got the right diagnostics, you've got a level of modularity that allows you to swap things out, because you're assuming that you're going to have failures. You're training and documenting things that are new, right? How to deal with high power electronics, how to deal with unique battery systems, how do you deal with cooling systems for batteries, etc. Right? And when we look at this challenge, just to put it into perspective, right? That chart is an interesting one. It's power density versus MTBO for the propulsion unit. So when you think about electric motors, where they need to be from a power density standpoint to be kind of efficient and useful in aviation is close up to where those aviation turbines are. And that means we're talking about Formula One car reliability, but I'm sorry, Formula One car performance with Toyota reliability, and how do you combine those two? So like I said at the bottom, easier said than done, but I do believe we've got the right minds and folks like yourselves working on this and going to prove that it can be done. So with that, I really appreciate everybody's time today. I hope this was helpful and informative, and I very much look forward to answering any questions you may have.
Thank you so much, Simon. That was incredibly informative and full of so much information. All of our participants on the webinar right now, please use the Q&A function in Zoom to post any questions that you might have. We have a couple right now that we'll start with. Let's see. In general, what are the costs for making devices or parts or structure modular to facilitate repair or replacement? Does this vary by system or component?
So let me just repeat that. So the costs for modularity, essentially.
Correct. For making the devices or parts, correct, to structure them for
Yeah.
modularity to facilitate repair or replacement? Does it vary by different components, different systems?
Yeah, I think so. So it's an interesting one because that's something that we're looking into in this NATO study that I'm chairing. So it's rotorcraft modularity for. So when it's done, welcome people to read our report. But ultimately, yes, depends on what we're talking about. But when we talk about mechanical modularity, so the ability to swap in, drive components, engines, etc. Typically the costs are associated with the interfaces. Um, Whenever you put a mechanical interface in place, you're generally inducing some type of weight and complexity cost that wouldn't be there if it was more integrated but not removable. So it's definitely one of these things that is a trade. And one of the ways you make that trade is you understand the predicted reliability of the component, the cost or benefit of having it modular versus not. What does that do from a maintenance standpoint? And you got to trade it off, right? And in the overall system balance, decide whether it's worth having modularity for that particular component. Um, Other things I think are inherently modular when we think about typical LRUs like power distribution units or other types of avionics boxes, etc. Those are fairly modular to begin with, so not um, not as difficult and not and your cost is already there. So I really do think probably your biggest trades are going to be in the mechanical side and deciding what pieces of the airframe or drive systems you want to make modular. Okay.
Is there an existing software that ties sustainment with your design and that can directly correlate the design to future sustainment costs?
Um, there are a number of logistical information system type software out there that allow you to kind of model this these types of trades, right? And essentially, the way I would characterize them as, would be, they're helping you bookkeep the reliability of components, the expected maintenance of certain maintenance activities, uh, and then essentially roll all that up and do the calculation to give you essentially what your uh, measurement could be for predicted mean time between failure, mean time between or maintenance man hours per flight hours, etc. Right. So there are some, I mean, like a place like Sikorsky uses a pretty sophisticated system. We actually designed and built ourselves. There are commercial versions out there that do similar. Slickwave, I think, is one of them that comes to mind, or Eagle is another. But for the most part, if you're talking about a smaller or less sophisticated or maybe less massive design than a 53K, you can generally do this sort of thing in just a spreadsheet. It's all about just um, documenting and keeping those types of things straight and keeping them up to date as your design evolves and making sure that you're refreshing those predictions as you make changes and that imparts different changes to your reliability factors, etc. So while I do think there are some software programs out there that can help, depending on what you're doing, you may be well served just to build it into a relatively sophisticated Excel spreadsheet. One of the benefits of doing it that way is you really understand the calculations and the numbers. Okay.
Could we say that a decentralized power distribution will be better than a centralized distribution? so we can't have a single point of failure, or can we have smaller battery size and then we can add batteries for redundancy?
I think that's a fantastic question, but it's not for me to answer, right? So that is your engineering trait right there. Um, and honestly, I'm not even the right guy to answer that. I don't have a background in power system design or propulsion design, electrical aircraft propulsion design. So I wouldn't be the best guy, but I would be the guy that said, "Yep, those are the questions we need to have the 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 right engineers in the room to talk to." And then, from a systems engineering approach, you kind of look at your different alternatives, roll up what your ultimate, sustainment metrics look like under each one of those alternatives, and make the decision. So that's probably not the answer that they want, but sorry.
Mhm. Great. Let's see. On what systems or components should we focus on? Which need sort of the earliest or most maintenance?
Wow, that's interesting too. So if I was doing this, yeah, you say historically on rotorcraft, right? Anything that vibrates, anything that moves, spins, those sort of things typically, are your maintenance headaches, right? So when you look at the origins of health and usage monitoring systems on big helicopters, they always started, or they started and focused on the drivetrains to start, because that was the biggest maintenance driver overall, the biggest had the biggest issues from a maintenance standpoint, reliability standpoint, also, from a system safety and operational safety standpoint, right? If the drivetrain fails, that's a bad day in a helicopter. It's not very aerodynamic otherwise. So, I would argue that the same thing is true here in the GoAERO platforms. The drivetrains, while different than maybe a turbine mechanical drivetrain, you're still going to have, I think, your biggest maintenance concerns in the drivetrain side, right? So I would be looking at the reliability and the failure modes of the motors, of the power control units, of the power distribution, um, and and focusing to ensure that you have, components that are going to be robust enough, to perform, to the reliability factors you're looking for. Some of the other typical stuff that we've seen in the past then comes back to, when I think about it, like a GoAir device, you're invariably going to be operating in pretty harsh conditions, right? It's not going to be a nice 70-degree sunny day. So, some of the other more insidious failure modes occur over longer durations, but, things like corrosion, choosing the right materials that are going to withstand the environments, whether that's temperature extremes, dust and sand, salt, etc., rain and water in ingress, except all that sort of stuff drives failure modes as well. So that would be the second thing I would look at, is your environmental durability. Okay.
Is any AI used in your field of work? Has it made an impact in sustainment or sustainability yet?
Yes. Simple answer. Absolutely. And I have told my team that, AI is one of these things that either we're driving the bus, we're on the bus, or we're under the bus, and we don't want to be under the bus. So yes, AI is coming in. What I will say, and I've said to my organization, is that right now AI is like a good, it helps you get to a draft quickly. right? You still have the need for subject matter experts, the need to uh, ensure you have quality, the need to ensure you have accuracy, etc. But we are seeing AI come into play when we do inspections, when we are looking at generating, um, technical publication changes from engineering changes. You can imagine there's a number of different places that AI is being and can be implemented, and rest assured that places like Lockheed Martin are not sitting idly by watching the AI revolution happen. So I'll leave it at that.
What would be the minimal sensor data to be captured from the aircraft when testing a VTOL aircraft to check for sustainability and determine flyability?
That's an interesting question. I think um, when we talk about sensor data for sustainment, so when we talk about health and usage monitoring systems, typically we're collecting, raw data that there is some type of correlation to um, either component or platform degradation over time. So what I mean by that is, um, you know, there's nothing magical here, right? It's typically accelerometers that are measuring vibration. It's temperature sensors. It is uh, in some limited cases stress, like strain type sensors, load sensors, that sort of thing. And so what you're actually doing is you're correlating your well, you're collecting sensors data to correlate your existing failure models. That makes sense, right? In other words, if you have a component that uh, fails after so many temperature cycles, then you're putting a sensor on that component and you're counting those temperature cycles. You're not relying on your predictions of how many temperature cycles it's going to go through. You're actually measuring it. And when you've measured those temperature cycles to a point where they start to approach your predicted number of cycles that result in a degradation, now you're flagging something. So there really isn't like a single answer to that question. It's more about um, understanding the different components that you want to be monitoring, and ensuring reliable operation, and then monitoring them for kind of these basic uh, parameters that you've already correlated to some type of failure and degradation model, right? So if you think about like in a drivetrain system, if you're putting a vibration sensor on a electrical motor, you've already run that motor in a lab to the point where it starts to fail, and you've recorded, say, the vibration changes in that motor as it's starting to degrade, so that when you've put that same sensor on that motor in your platform, as those signatures start to come out of that sensor, you now know that, oh, wait a second, in the lab, when this thing started vibrating at this level, we knew it was pretty close to being done. Well, now on the platform itself, you can now make that prediction. Now, I know my prognostic friends probably have rolled over in their grave with that explanation, but it's a simple way of explaining kind of what we're doing there. So again, it's not magic. It's about, you know, taking actual measurements and trying to correlate them back to known failure and degradation modes of the constituent parts that you're trying to keep an eye on. So hopefully that makes sense. Any
Thank you.
other questions?
We're actually at time, Simon.
Okay. Yeah.
So I think
Yeah.
we'll
Time
wrap
flies
it
when
up.
we're having fun.
Absolutely, yeah. Thank you so much again for joining us today. We really appreciate it. And all of our participants, remember that you can view the recording of the lecture at herox.com/GoAERO. And we encourage you to complete your registration for the competition if you haven't done so already. And we look forward to announcing our lectures for August in the coming days. Thank you again, Simon. We really appreciate your support and your time here today.
Yeah, this was fun, fantastic. Thank you, everybody else, for their time and attention. Bye now.
Take care.